This video is going to go through the derivation of the equation for centripetal acceleration. In class, I just threw the equation at you and shows you that it works by the units, but here I'm going to go through all the geometry and the algebra to show why it happens that way. I would like you to take notes on this, and you notice that this picks up right where we left off in class. Here's our picture of the top-down view of a passenger in a car making a right-hand turn. The passenger's head here is shown by the circle. Here's the initial velocity vector, them going straight, and then here's the time, sometime later, the same head, with the same speed. Remember, we're going at a constant speed here, but we changed direction. So this is V0, this is VF. And I show here that V0 equals VF in magnitude, which I designate by using the absolute value bars. The problem came when we tried to use the linear acceleration equation. Our original equation is delta V over t, and since VF and V0 are the same thing, this would give a zero acceleration, which does not make any sense, because clearly there is an acceleration because there's a change in direction, even if there's no change in speed. So our old version of the acceleration equation just doesn't work. So we need a new version. So we start by using the equation that delta V equals VF minus V0. Let's rearrange that to show that VF equals V0 plus delta V, then put the vector arrows above it to indicate this is a vector addition. If it's a vector addition, then we can show this as a vector diagram. So here's the initial velocity V0. VF would be the resultant of adding V0 plus delta V, so I show VF as a blue vector. In your notes, of course, you want to show it as maybe a different color or a bolder vector, whatever works for you. The only thing remaining is delta V, which then would have to be here to complete the triangle. So it says V0 plus the vector delta V equals the resultant VF. No change in magnitude, but a change in direction. Let's take this from a different perspective. If we go back here to our picture, we see here's this dashed line is the tracing out the path length or the arc length traced out by the person that completes parts of the circle. So let's build up a picture of that over here. So here's the arc length, that same dashed line, which we call delta S, the arc length. And then relating that to R, this is the radius of the circle, this would be the center of the circle. And here's delta theta, the angular displacement through which the person moves as the radius vector. We want to think about it like that. Sweeps out an angle delta theta. Let's consider in this picture here in shorter and shorter time intervals, where it only goes a smaller portion of the circle, or a smaller portion of the circle, or even a smaller portion of the circle, going from this position to this position, where delta theta becomes smaller and smaller and smaller. You notice that as delta theta becomes smaller and smaller, what looks like here to be the wedge or piece of a pie approximates a triangle. This path length, while it's still curved, is getting closer and closer to being a straight line. I want to make it look like a straight line, imagining this to be smaller and smaller and smaller, because now we have a triangle made out of delta S and R. In fact, it's an isosceles triangle, since R, of course, is the radius, and that's not going to be any difference. This delta theta could also be considered to be this delta theta in this triangle, which also is isosceles, since V0 and VF are the same. Remember, it's a constant speed. And as delta S gets smaller and smaller, well, the difference between these two velocity vectors is going to get smaller and smaller as well. So we can say this small angle is the same as this small angle, and now we have two isosceles triangles made up of the same delta theta. We have congruent triangles. We can relate parts of these to be equal to each other. Once we say that V0 equals VF equals just the common speed V. So if we set this ratio here, delta V over V, that would be like the base of the isosceles triangle to one of the sides of the triangle, where we're calling either one of these sides just plain old V, like over here. The base over the side is going to be the same as delta S over R. Delta S over R, the base over the side there as well. Now delta S is really like a distance, and like a delta X, so delta X equals V bar T. So I can replace delta S with V bar T over here. But remember, it was going at a constant speed, so we can get rid of that bar. Just write it as V. And now we just play a little bit of an algebra game. We're going to take this T over here and put it on the bottom. Take this V and put it over there. So now we have delta V over T equals V times V, which is V squared over R. And hey, V squared over R should look awfully familiar. Delta V over T is, of course, acceleration. And now we have our equation that centripetal acceleration equals V squared over R. The book goes through a very similar derivation. Of course, you could also just watch this video again if you'd like to see it again.